Hello, hello Nagendra. Yeah, we will start. We will wait for 10 minutes. We will see if anyone other joins. Then we will start. Okay. 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 I think that time is same. Okay. 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 No problem. Okay. Okay, so I think no one is going to join. We will start. So my name is Ganesh Shankar Bhandari, and I am TA of Principal of Casting Technology, taught by Professor P.K. Jha from IIT Roorkee. So we are doing live session for week 6. So first, we will discuss about the cast iron, types of cast iron. There are mainly four types of cast iron, which is known as gray cast iron. Then coming to second one, white cast iron, nodular cast iron, which is also known as ductile cast iron, and the last one is malleable cast iron. So these four types of cast irons have different properties and different advantage, disadvantage of their, and they also have different manufacturing routes, how they manufacture, and they have different properties. Although we know that cast iron generally contains their properties due to the presence of graphite in their structure, but the characteristic of that graphite structure defines the properties of those cast irons, which is uh, divided into these four parts. I think someone wants to join. Okay, so coming to the explanation of each cast iron. So first we will discuss about gray cast iron. Okay, so in the gray cast iron, what we know that graphite presence in this type of cast iron is in the form of chips like structure. As you can see in this graph, these are in the form of flakes. Okay, so what these flakes do, these flake provide the necessary properties to our cast iron, which is mainly as a damping capacity of that cast iron. Okay, these types of cast iron have very high damping capacity because these flakes provide the necessary strength for those damping applications. So generally you can see this type of cast iron plates used beneath the your lathe machines. Okay, because they have very high shock resistance properties. So you can use them as the base for your heavy machineries. Okay, so these graphite chips also act as a tool lubricant. So these types of cast iron generally majorly used in the tool applications also, and these have very high damping capacity. So coming to the advantage of this type of gray cast irons, the graphite act as a chip breaker and a tool lubricant. These are very high. These have very high damping capacities. These types of cast iron also have dry bearing qualities due to graphite presence in those in the structure. And after formation of protective scales, it resists corrosion in many common engineering environments. So whenever you are going to provide generally this type of cast iron also used in the uh, oil industries to transfer the oil. Okay, petroleum industries use this type of cast iron because it has very high corrosive resistance, so it is not going to react with your oil. So you they use these type of cast iron to make the pipes. Okay, then coming to the next one, white cast iron. So as you can see in this graph, in this micrograph, the in this carbon is present as a not present as a flake, as we have seen in the last photograph of gray cast iron. It is present in the bulk. Okay, it is present like a structure which is known as carbide. Okay, so carbon is present in the form of carbide in these types of cast iron, and these types of cast iron have very high abrasion resistance due to the presence of carbides, because carbides have a better abrasion resistance properties compared to graphites, because generally graphite shows uh, some friction less frictional properties. Okay, generally we use graphite in casting processes for making the fluidity of your molten metal wetter. Okay, so graphite does not have as much resistance capacity, abrasion resistance capacity compared to your carbides. But apart from abrasion resistance, these are very brittle in nature because due to the carbide iron carbide formation in the structure of white cast iron. So then coming to the next one, the advantage of these cast irons, as we discussed, these are very hard, very brittle in nature, but they have very excellent wear resistance properties. But brittle in nature because large amount of iron carbide formation in the structure, and these types of cast iron made by the rapid cooling of gray iron, because if you are going to cool down that gray iron in a very slow manner, then it will have the time to deform that graphite structure into graphite flakes, but you are not providing any time to get that graphite diffuse out from the structure, so it will be in the form of iron carbide only, so we can get our white cast iron. Coming to the next one, this is the structure of micrographic structure of a nodular or ductile cast iron. Okay, why we call this as a nodular cast iron? Because the graphite is, yeah, okay. Hmm. Actually, only carbon carbide is there because you are not providing the sufficient time, because when you are going to melt it down, so when you are going to put your graphite percentage or carbon percentage of around 4 to 5%, typical concentration of cast irons, so that will be in the form in the beginning, that will be in the form of iron carbides. Okay, at higher temperature it will form iron carbide, and when you are going to cool it down, okay, so that iron carbide will decompose into iron ferrite and your carbon structure. Okay, Fe3C will get converted into Fe plus 3 carbon, 3 Fe plus carbon structure. Okay, so when you are going with the rapid cooling of that iron, so it will not going to have that much time that iron or carbon is going to diffuse out from the structure of iron carbide. Okay, so that will remain in the form of that iron carbide only, then you are going to get your white cast iron. But if you are giving sufficient time during cooling down process, we can say if we are going with annealing process, then you are going to form that gray cast iron. Okay, understood. Yeah, you can say that during heat treatment, or when you are going with the casting process, if you are going with maybe continuous casting process, then you can get white cast iron, or if you are going with the very low conductivity type of mold, okay, you are going your molding process with very low conductive mold. Okay, so the heating, the solidification time will get increased. Okay, so that if you are going to increase your solidification time, so you will get very you will not get rapid cooling rates, so you are going to get white gray cast iron. And if you are going with a permanent mold, maybe some mild steel mold or metal mold, then it will be having very high conductivity. Okay, so it will get converted into that white cast iron due to rapid cooling rates of gray iron. Okay, coming to the next one, nodular cast iron. So, as the name suggests, the graphite will be in the form of nodules. Okay, you will get spherical carbon nodules in the structure of cast iron. So, it is known as nodular cast iron. So, the properties. So, how we are going to get these nodules of graphite in the structure? Okay, when we, because we are talking about flake formation of graphite, or it is going to convert into iron carbide. So for making these spherical carbon nodules, we have to add some alloy materials. Okay, some alloying elements in your in the structure of that cast iron. Okay, so we are during melting process, we generally add cerium, magnesium or sodium inside our structure as a foreign elements. So with the help of these foreign elements, that spherical carbon nodules will be going to form inside your structure. Okay, but the major challenge is that you have to go with very low sulfur content iron. Okay, you have to minimize the sulfur content in that iron, uh, less than 0.05 percentage, because if sulfur content is there, then it is going to create iron sulfide in the structure, and you will not get the desired properties in your ductile cast iron, because iron sulfide is going to provide some brittleness to the structure. Okay, it will cool down at the grain boundaries of that structure. Okay, so you will not get the desired properties. It will produce more brittleness compared to ductile cast iron. Okay, so you are going to add some alloying elements like cerium or magnesium. In major foundries, they use magnesium and cerium as alloying elements for making these spherical carbon nodules in the cast iron, and these possess very high ductility compared to other cast irons. This type of cast iron possesses when going with the elongation properties. When we are talking about elongation properties, that can go up to 18 to 25% elongations, while other types of cast iron cannot go more than 10% of elongations. Okay, so as the name suggested, it is known as cast iron, and it possesses high elongation properties. Okay, so coming to the next one, that is malleable cast iron. So how we are going to create this malleable cast iron? For creating malleable cast iron, first we have to create white cast iron. Okay, uh, then we are going to heat treat that white cast iron at around 1700 degrees Celsius, and very slow cooling will be provided to that cast iron. We will go with annealing process. So during that annealing process, what will happen, that iron carbide presents in the structure of white cast iron, whatever the iron carbide is remaining there, um, most of the in white cast iron, most of the graphite will be mainly present in as uh, carbide. So that iron carbide is going to break down into ferrite and free carbon structure, which is known as which we will termed as tempered carbon. As we can see in this graph, in this micrograph, there is tempered carbon presence is there. So due to the presence of this tempered carbon, we will get some malleable properties, as the name suggests, malleable cast iron. So we can convert that cast iron easily into the sheet structure. We can't go with other cast irons to convert them into sheet, because they don't have that much ductile properties. Okay, but this type of cast iron we can convert them into sheet structure. So these are known as malleable cast irons. So graphite flakes are not going to form inside these types of cast iron, because we are going with very rapid cooling. Okay, so we are not providing the time to diffuse out of carbon from the structure. Okay, so major disadvantage of advantage of these types of cast irons are they have excellent machinability properties, then significant ductility are there, and good shock resistance properties. However, some major disadvantages are there. These types of cast iron have very high shrinking properties compared to other ones during solidification process. Okay, so you have to provide some riser system, and you have to go with very high shrinkage uh, allowances in your during your casting processes. That is the major disadvantage of these types of cast irons. So these are all about the cast irons, whatever we have read in the lectures. Now we will go with some MCQ type of questions. And okay, so coming to the first question, if basic slags are formed during melting operations in furnace, the refractories used in furnace should be acid refractories, are So anyone wants to answer? If we are going with the basic slag practice, what we are talking about in when we are going to smelt down our material, because there are two things. One is melting and second one is smelting. Okay, both processes are same, but they have different meanings behind these words. In melting processes, when we talk about only melting, okay, so we can talk about the recycling of aluminium. Okay, for example, if we are talking about recycling of aluminium, so we just have to melt it and we have to cast it again according to our desired design. Okay, so that we can say as melting of that aluminium. But when we are talking about smelting, then smelting is basically defined as slag plus melting. Okay, so we are talking about slag formation during melting process. There are some impurities inside your material, whichever you are going to melt down. When we talk about the recycling of steels, okay, we smelt them in the generally we smelt them in electric arc furnaces. Okay, so we go with the slag formation. Okay, because there are some impurities inside that stainless steel. There are some manganese content. There can be chromium content. More major alloying elements can be there. Okay, so if you are trying to convert them some other type of steels with having some other compositions, okay, so you have to form the slag. Okay, so smelting is defined as slag plus melting operations, and during smelting operations we go with the two types of slag practices. First, we will go with basic slag practice, or second we will go with acidic slag practice. That will depend on the material whichever is going to report into the slag. It's like if we are talking about phosphorus, then it will uh, be your basic slag. It will form the basic slag, and if we are going with the slag formation of sulfur, okay, so it will form acidic slag material. And if we are going with the aluminium or silicon slags, then it will possess different properties. Okay, so there are majorly two practices are there during smelting operations in furnace. One is basic slag formation and second is acidic formation. So according to that slag formation practice, you have to design your refractories of your furnace. Okay, so anyone wants to answer this question? Okay, no one. So when we talk about refractories, okay, so what comes in our mind? Uh, it has to have very high melting points, okay, and it should be inert in chemical reactions. Okay, when we are talking about chemical reactions, it should be inert. Okay, so when we are talking about basic slag practice, so if we are going with acid refractories, okay, what will happen, that basic slag will react with those acid refractories. Okay, because that is universal truth that any base is going to react with your acid to form salts. Okay, so we can't go with basic slag formation in acid refractories. Okay, so in that case, in basic slag formation, we have to go with basic refractories only. Okay, so that basic refractories can be of magnesium carbonate or calcium. You can go with calcium carbonate. So magnesium or calcium refractive bricks you can use in that melting operations. Okay, if you are going with acidic slag formation, then you have to go with acidic refractories. Okay, so the answer will be, if basic slags are formed during melting operations in furnace, the refractories used in furnace should be basic. Okay, coming to next question. It will react with your acidic lining, because that is universal truth that any base is going to react with your acid. Okay, to neutralize that content. Okay, basic base plus acid equal to salt. Okay, so that will affect your refractory lining, and you have to change that refractory lining. It will, uh, it can, you will have more slag formation inside that, and your refractory lining is going to break. So your furnace is not going to work, because refractory linings are there to prevent the temperature inside that furnace. Okay, and outer body of your furnace to not get melted. Okay. Okay, coming to next one. Which of the statement about the continuous casting is correct? The mold is generally made up of copper. Casting yield is very high. It is more suitable for casting with irregular shape and cross sections. So, anyone wants to answer? No, I don't think so. B is right. Okay. So, when we are talking about continuous casting, we talk about mold is generally made up of copper, because copper has very high conductivity, and uh, but the thing is that copper has a melting point of only 1040 degrees Celsius. Okay, but you generally go in the continuous casting process. We generally go with the casting of mild steels. Okay, and it has a temperature melting temperature of around 1400 degrees Celsius. So what comes in mind, that copper is going to melt. Okay, because copper has a melting point of 1040, and we are going to pour that molten metal inside that copper mold at a temperature of around 1600 to 1700 degrees Celsius. Okay, but what we do generally do with this copper molds, we provide a continuous flowing water jacket, um, which is going to cool that copper mold, so it is not going to melt down. Okay, so that is due to that water jacket, continuously flowing water jacket, you will get very high conductivity of so that whatever the material is coming from 1700 degrees Celsius pouring temperature, it will come down instantly to around 600 or 700 degrees Celsius. So your material is going to solidify very quickly. Okay. So due to that high conductivity, we generally go with the copper mold. Okay. Then coming to the second point, casting yield is very high. So when we talk about casting yield, it's about how much amount of the material we are going to pour. Okay, and how much weight of the casting we are getting. Okay, so in the case of continuous casting, when we are talking about continuous casting process, so casting yield will not be that much high, because the scaling formation due to the oxidation process, that will be major at that point. Okay, because your mold is at very high temperature. Okay, and it is not surrounded by anything. Okay, so it is in the direct contact of your air, so it is going to oxidize continuously. Oxidation process will be there, so chip formation on the surface will be there. So casting yield, you will get around 70 to 80% most probably. So that I think cannot be true. Casting yield is not that much, not we can say that it is very high. Then coming to the third point, it is more suitable for casting with irregular shape and cross sections. Yes, we can say that it can be used suitable for casting with irregular shape or cross section. Generally, in the continuous casting process, what we talk about, we generally just think we are going to make bloom or billets type of thing. Okay, or we are going to some seed formation during that continuous casting process. But your rails. Okay, rail, that rail is also a product of your continuous casting process. Okay, so that have a very irregular shape, and that has some cross sections. Okay, so that is also produced with the help of that continuous casting operations only. So it is more suitable for casting with irregular shapes and cross sections, yes, but much complex. Okay, we are not talking about complex shapes, but we are talking about irregular shapes having very high length. Okay, so the answer will be both A and C. Okay, any doubt? Okay. Coming to the next one, infinitely long billets or slab can be cast using die casting process, investment casting, continuous casting, or centrifugal casting. Yeah, this is easy one because we have already talked about continuous casting process. So when we are talking about infinitely long billets, so we will go with continuous casting process. Okay. Coming to next one. Which of the following furnace ensures carbon peak during melting of gray iron? Cupola furnace, induction furnace, open hearth furnace, or electric arc furnace? So we are talking about carbon peak during melting of gray iron. It means we are um, adding some extra carbon into that material during the smelting or melting process. So which type of furnace we generally go with for ensuring carbon peak during melting of gray iron? Yes, it is cupola furnace. Because in cupola furnace we generally use coke. Okay, coke or carbon as a heating source. Okay, so it will be easier to pick the carbon during melting of gray iron because we are going with the coke. Okay, in induction furnace we generally provide the heat with the electricity, okay, via induction process. And in open hearth furnace we generally go with the oil burning, or if we are burning with we are going to heat it with some carbon also, then we generally go with the gaseous formation. Okay, we form gas from the carbon and we are going to provide in open hearth furnace as a fuel. And electric arc furnace we provide the temperature with the help of arc formation via high electricity voltage around 11,000 volt or something like that. We are going to provide into those uh, electrodes, and due to resistance it will create the arc which will be having a temperature of around 4,000 to 5,000 degrees Celsius. That will help to smelt your material. Okay, then coming to the next one, which of the following is the purest form of iron? Cast iron, pig iron, wrought iron, or stainless steel? Pig iron? No, I don't think so because we are talking about purest form of iron. Because pig iron contains I think carbon percentage of around 3 to 4%, which is generally produced by the blast furnace, and you are going to convert that pig iron into your mild steel or stainless steel after that process. So when we are talking about purest form of iron, okay, we are talking about around 99 or more than that percentage of iron. Okay, so in cast iron, we generally go with a carbon percentage of 3 to 5% depending on your properties. We can go with graphite formation, and we can go with iron carbide formation. Okay, in case of wrought iron, we this is the purest form of iron, uh, which is generally formed during generally this type of iron found as what we can say, it is generally found as naturally also sometimes. Okay, so that is known as wrought iron, and in case of stainless steel we go with the alloying elements around 10 to 15 percent of alloying elements can be there. So the purest form of iron is wrought iron. Okay, then coming to next one, carbon equivalent is defined as. So anyone wants to answer? So we are talking about carbon equivalent. Okay. So with the term equivalent, what comes in mind? It's like having similar properties with carbon or something like that. So what the carbon do in your gray cast iron or mild steel structure? It is going to provide some alloy formation, like it can provide you iron carbide in the system, or it can provide you graphite in the system in the form of nodules or in the form of flakes. So what is it is going to add up in your casting? It is going to add a property which is known as toughness, or we can say brittleness in your system. Okay. So this type of properties in your iron or mild steel system can also be provided with the help of silicon and phosphorus, because these are also going to provide you some brittleness in the system. Or we can say phosphorus can provide you fluidity in the system, and carbon can also provide you the fluidity in the system during your molten conditions, because it if it is in the form of graphite, then it has a excellent fluid properties. Okay. So phosphorus is like that, that is also going to provide you some brittleness in the system or fluidity both at the same time. And silicon can provide you the brittleness in the system if you are going with iron silicate formation, or it can provide you silicon carbide in the form. Mm, okay. So when we talk about carbon equivalent system, carbon equivalent is defined as, so whatever the carbon is there, that will obviously provide you some brittleness, and the Si and phosphorus in the combined form is also going to provide you the same properties of brittleness or fluidity according to your need. So the carbon equivalent is defined as carbon equivalent weight percent equal to carbon plus silicon amount plus phosphorus amount divided by 3. Okay. So that is going to be your carbon equivalent. Okay. So coming to the next one. Which of the following statement is are correct? First one is the flakes of graphite have good damping characteristic and good machinability. The flakes of graphite also are stress concentrators leading to high toughness. Phosphorus in cast iron is known to contribute towards good fluidity of melt. So anyone wants to answer? One of the point we have recently discussed in previous slide. Huh? B, D. Okay, first, second, and third. You are saying all are correct. Okay, we will see. So we will go with one by one. The flakes of graphite have good damping characteristic and good machinability. We know that because we have already discussed about gray cast iron, which is having high damping characteristics, very high damping properties, and they have also good machinability, and that is formed due to the presence of flakes of graphite in the system. Okay, so this one is true. Then coming to the second point, the flakes of graphite also are stress concentrators leading to high toughness. Okay, so that is not going to be true, because we are talking about damping properties. Okay, so damping properties and stress concentrations are vice versa to each other, because if there will be more stress formation in the structure, then it will not show you the damping properties, good damping properties. Okay, because you are talking about shock resistance. Okay, if the stress concentration will be high there, then it will cause the brittleness in the system. It will not lead to high toughness, it will lead to brittleness in the system. Okay, if stress concentration is high there, so the flakes of graphite will not access stress concentration, and it will not lead to your high toughness of the system. So that is not going to be true. Then recently in we have discussed in the previous slides only, the phosphorus in cast iron is known to contribute towards good fluidity of melt. Okay, Uh, Generally, it can be provided by both of phosphorus, or it can be also provided with the help of graphite in the system. Okay, so that will provide you the good fluidity of the melt. So that is also true. So the answer is first and third only. Okay. So coming to next one, which of the following statements is are correct? White cast iron is the starting material from which malleable cast iron is produced by annealing. The structure of white cast iron consists of massive carbide and pearlite. So we have already talked about white cast iron and how it is made, and we have also talked about malleable cast iron. Yes, first one is correct. Yeah. Okay. So, when we talk about malleable cast iron, we talk about white cast iron. First, we are going to form the white cast iron, and we are going to heat treat it at around 1700 degrees Celsius, and we are going to slowly cool down it in the furnace itself. So that will provide the sufficient time for conversion of for the formation of iron carbide into the system. Okay, so that will, your malleable cast iron can be produced. So that point is true. Then coming to the second one, the structure of white cast iron consists of massive carbide and pearlite. So carbide is basically your Fe3C, okay, and pearlite is a structure basically that will consist Fe3C and Fe layer. Okay, that will be like layer formation. Fe carbide layer, one layer of Fe carbide, then a second layer of ferrite, then another layer of Fe carbide. That is like the structure on the back of zebra. Okay, strips like structure. So that pearlite is that structure. So due to that layer like structure, what property you are going to have, if the iron carbide is only present there, then you are not going to have the ductile properties inside the system. But if the pearlite formation is there, then you will be going to have excellent ductile properties in your system and excellent strength, because what will happen, uh, it will be like ferrite layer, then iron carbide layer, then ferrite layer, iron carbide layer. So during the stress concern, when you are going to apply some stress on the material, so that iron in that case iron carbide is going to resist. Okay, through Fe ferrite you are going to move freely, but when the stress burst at the iron carbide layer, it is going to resist that. So you are going to get better toughness in the system. So the structure of cast iron consists of massive carbide and pearlite. Yes, because uh, we are not providing the enough time. We are not providing enough time for iron carbide, or we can say for graphite to fully convert into your iron carbide system. Okay, so that will consist of iron carbide and iron both. Okay, so we can say that we are going to have a pearlite structure in that system. Okay, so the answer will be both first and seconds are correct. So understood, or any doubt regarding pearlite? Yeah. Okay, so coming to the next one, which of the following statement is are correct? In the process of controlled annealing, The metastable phase of white cast iron decomposes into free carbon and iron as represented by the reaction. Second one is the structure of malleable cast iron consists of aggregates of temper carbon in a matrix of ferrite. Okay, any answer? Okay, so when we are talking about a word metastable phase here. Okay, in our iron carbide, as iron carbide, which is also known as metastable phase. So when we talk about phase system, okay, we generally talk about iron carbide phase diagram, iron carbide phase diagram. So there are different phases in that iron carbide system. Uh, that changes according to the temperatures. Okay, so when we talk about we one phase is there, we talk about austenite phase. Okay, so that phase is stable at around more than 750 degrees Celsius to 950 degrees Celsius. You are going to get that phase, austenite phase. We talk about austenite phase. So that phase is not stable at room temperature. Okay, that is going to you are going to get that phase at around 750 to 900 degrees Celsius to 1000 degrees Celsius. And when you are going to decrease the temperature from that 750 degrees Celsius, so that phase will not be there. Okay, austenite, you are not going to get austenite at room temperature. Okay, so that type of phase is known as metastable phase. And what is the stable phase in the system? That is generally iron. Okay, because on at room temperature you are definitely going to get the iron. And one more thing is there, that will be carbon. Okay, so these two phases always will be there. Okay, so these two phases are generally known as stable phases in the iron carbide system. Other phases whatever is there, those are known as metastable phases, because according to temperature those are going to get converted into some other things, or that it will also depend on your process kinetics. If you are going with annealing process, you are going with mar tempering process or os tempering type of process, so that will also depend on that thing. So that metastable phase is going to convert into what type of phases. So one phase is there, iron carbide, which is Fe3C. Okay, so that is also known as metastable phases, because according to your process, you are going with annealing, or you are going with quenching process, or you are going with os tempering process, that iron carbide phase is going to convert. Okay, if we are when we are talking about annealing phase, so what will in annealing, we are talking about very slow cooling. We are going to heat treat our cast iron or whatever we want to heat treat at up to 1500 or 1600 degrees Celsius, or we can say around 900 or 1000 degrees Celsius. And then we are just leaving that material into the furnace itself. Okay, as slow the furnace is going to cool down, your material is going to cool down. Okay, so when we talk about annealing process, it will take very high time to get cool down from that particular temperature to the room temperature. That can sometimes that can take around 24 hours or more than 24 hours also. But if we are going to get that material outside the furnace, maybe it can get cooled down in maybe 2 or 4 hours or 6 hours itself. And third thing is quenching process. So in that quenching process, what you are going to do, you are going to take out that material at that particular temperature of 800 or 900 degrees Celsius, and you are going to put down that material in cold water, which will be having a temperature of around 5 or 10 degrees Celsius, or you can talk about frozen water also. subcritical temperature water also, that can be at around -20 or -10 degrees Celsius. So you are going to put that down in that water. Okay, so from that 800 or 900 degrees Celsius temperature to room temperature, it will take some few seconds to get that temperature down. So that is known as quenching process. Okay, so according to that process, your meta-stable phase will be going to change in other phase. Okay, so iron carbide phase, if we are talking about annealing, so iron carbide phase will get converted into from Fe3C to iron and free carbon. Okay, so that will be like Fe3C is going to converted into 3 moles of iron plus free carbon system. So in the process of controlled annealing, the meta-stable phase of white cast iron decomposes into free carbon and iron as represented by the reaction. Uh, that will be like this. Fe3C is going to convert 3Fe plus C. So that reaction requires a time, okay, to get for get, diffusing out of carbon, you need time and temperature both. So in annealing process, we are providing the both things. We are providing time and we are also providing the temperature at the same time. Okay, so that carbon is going to diffuse out from this Fe3C system and it is going to get converted into 3Fe plus carbon. So as we have already discussed, white cast iron decompose into free carbon and iron as represented by the reaction, and it will be going to create the malleable cast iron, okay, during that annealing process. So this point is correct. Second one is the structure of malleable cast iron consists of aggregates of temper carbon in a matrix of ferrite. Yes, we have already talked about, we are going to get iron plus carbon during that annealing process. So the structure of malleable cast iron consists of aggregates of temper carbon in a matrix of ferrite. Yes. So the answer is both first and seconds are correct. Understood? Okay. Can we proceed? Okay. So coming to next question, which of the following statement is are correct? Fluidity of alloy steel is lowest compared to cast iron. Then second one is casting of alloy steel is relatively easier than that of cast iron. So answer wants to answer this? Okay, so previously we have talked about fluidity uh, according to the presence of graphite in the system. Okay, so when we talk about fluidity, what comes in mind? That fluidity is directly proportional to, in case of casting process, when we talk about fluidity, we talk about superheat. Okay, so superheat is like your melting temperature of some alloy or whatever you are going to cast is around 1400 degrees Celsius, but you are pouring it at a temperature of around 1600 degrees Celsius into your cast mold. Okay, So that pouring temperature is directly proportional to your fluidity. Okay, one thing is that. Second thing is, mm, when we talk about fluidity, we also talk about freezing range. Okay, so that is in the beginning when we talk about just we are going to pour your material inside the mold, we are talking about pouring temperature or superheat. But inside the mold we will talk about the freezing range of because inside the mold the fluidity of the metal will depend on your freezing range of that alloy or whatever the pure material or whatever material you are going to cast. So that that fluidity is inversely proportional to your freezing range. It means if your freezing range is very high, okay, very vast, then the fluidity will be more. If your freezing range is uh, lower, then fluidity will be less. So when we talk about alloy steels, so we are talking about elements added into that steel. So those what those elements will do, those elements will provide foreign particles, okay, to the systems. Okay, so due to those foreign particles or the alloying elements inside the system, what will happen? The solidification will start as early as possible because they are getting the surface to form the nucleations. Okay, when we talk about solidification, we talk about nucleation and growth phenomena. So those alloying particles or alloying elements will be having the different uh, melting points or freezing points. Okay, when we talk about copper, it has a melting point of around 1040 degrees Celsius, and we talk about steel, its melting point is around 1400 or 1500 degrees Celsius. For example, if we are going to add the copper into your steel system as a alloying element, so what will happen when you are going to pour it? That copper is going to solidify first, okay, due to low temp melting temp, and you will get the uh, foreign particles to start the nuclei formations. Okay, so fluidity of alloy steel due to that because your freezing range is going to coincide. So according to that, the fluidity of alloy steel will be going to lower as compared to cast iron. Okay, so this statement is true. Then coming to the second statement, casting of alloy steel is relatively easier than that of cast iron. Okay, so we have already talked about fluidity of alloy steel, which is lower as compared to cast iron. One more thing is there in cast iron, you have graphite. Okay, so graphite is going to provide more fluidity to the system due to less frictional properties inside the system. So that is going to provide you the high fluidity in the system in case of cast iron. So that thing is there. Then coming to second point, casting of alloy steel is relatively easier than that of cast iron. So when we are talking about casting, so in case of casting, we need high fluidity. Okay, because if we are going to make some intricate designs, okay, some complex designs, so we need high fluidity in the system. Okay, so if system will not be having the high fluidity, your casting will not going to be easier. Okay, so here statement is casting of alloy steel is relatively easier than the of cast iron. No, the casting of cast iron is always easier compared to your alloy steel because it is having higher fluidity. Okay, so casting will depend on your fluidity. So the answer is only statement first is correct. Okay, any doubt? Okay, coming to the next one. Which of the following statement is are correct? The presence of phosphorus lowers the melting point and improves the fluidity of the metal. Then second one is sulfur is generally present as iron sulfide. So we have already talked about these 2 points earlier. So anyone wants to answer? Yes, both are correct. Because The presence of sulfur is going to lower your melting point, because what will happen, it is going to create some iron phosphate particles inside your system, and the iron phosphate has a lower melting point compared to your iron carbide or iron system. Okay, and it will improve the fluidity of the metal. Then coming to the second one, sulfur is generally present as iron sulfide. Yes, it is also true. So answer is both first and seconds are correct. Okay. So next question is steel containing 0.8% carbon is known as. So you have learned about the iron carbon phase diagram system, iron and iron carbon phase diagram. In that iron carbide system, one point is there where we are talking about 0.8% carbon. So that type of steel known as, that is the straightforward one. So anyone wants to answer? Okay, yes. Uh, that is basically eutectoid steel. Okay, at 0.8% carbons and around at 725 degree Celsius temperature. From at that 0.8% carbon we talk about when we are going with 725 degrees Celsius of temperature. Then from that temperature your perlite is going to convert it into austenite phase, which is basically metastable phase. And if you want martensite in your system, then you have to rapidly cool down that uh, steel after heat treatment to up to that temperature to form the martensite in the system. So we talk about eutectoid steels and we talk about eutectic steels in the systems. Okay, so point with 0.8% carbon, that is known as eutectoid steel. So coming to the next one, steels containing less than 0.8% carbon are termed as eutectic steel, hypoeutectoid steel, hypereutectoid steel, or paratectic steel. Yes. No, because when we are talking about eutectic, paratectic, or eutectoid steel, we are talking about that particular point. Yeah, it can be hypoeutectoid steel because we are talking about less than 0.8% carbon. So when we talk about less than zero point 0.8, that will be your hypoeutectoid steel. And it is, if it is going to more than 0.8% carbon, okay, then we will talk about hypereutectoid steel. Okay, at eutect, when we are talking about eutectic steel, that will be the particular point at that particular temperature only, then you are going to get that eutectic steel or paratectic steel. Okay, coming to next one, which of the following statements is are correct? High refractoriness value of melting molding sand is used in steel casting due to its high pouring temperature. Then second one is no carbonaceous material washes can be used on the mold faces in case of steel casing, as it tends to dissolve in the system molten metal. So anyone wants to answer? You are saying both are correct. Am I right? Okay. So both are correct here. Because when we talk about high refractoriness, why we need high refractoriness? Because we don't want to uh, lose the shape of that mold, or we don't want to uh, destroy the refractory linings. Okay, so when we are talking about steel casting, we are talking about a temperature of around 1700 degrees Celsius, and for that we need some high refractory material which can have a melting point of around 3000 or more than that melting temperature. So yes, high refractoriness value of molding sand is used in steel casting due to its high pouring temperature. And the second one is no carbonaceous material washes can be used on the mold faces. So why we use this carbonaceous material on the mold faces? To provide the fluidity to the system. We When we talk about gating or gating systems, we talk about graphite coating on those gating systems. Okay, so your material is going to um, have some high fluidity inside the system by avoiding the frictions with the mold wall faces. Okay, but we cannot use carbonaceous material as a washes on the mold faces of the system, because what will happen, steel has a tendency to dissolve the carbon inside the system, and it will uh, going to maybe enhance or decrease the properties of your steel casting, so that you don't want. Okay, then coming to next one, stainless steel contains iron and carbon, iron, carbon, nickel and chromium, chromium and nickel, and iron, carbon and nickel. Yes. So iron, carbon, nickel and chromium, all four used in stainless steels. When we talk about only iron and carbon, that can be mild steel or that can be cast irons only. Okay. So when we talk about mild steel or cast iron, we talk about only iron and carbon. In case of stainless steel, we add some alloying elements like nickel and chromium inside the system. So why we are adding this nickel inside the system? We want uh, by the adding of nickel, we provide some toughness. Okay, we provide some extra strength to our stainless steels, and we talk about lowering the heat treatment temperatures. So what will nickel do? Nickel will stabilize the austenizing temperature of that stainless steel. Okay, so that is going to bring down the austenitic conversion temperature from 750 degrees Celsius to maybe it can come down to 200 or 300 degrees Celsius, whatever you want. So that is going to provide some extra toughness to the system. And what will chromium do? The chromium will provide a coating on the surface of that stainless steel. So your steel is not going to corrode easily. Okay, in case of mild steel, when we talk about mild steel, we don't talk about corrosion resistive properties, but in case of stainless steel we talk about corrosion resistance properties. So chromium is added for that, uh, providing the corrosion resistance properties to the stainless steel system. Okay, so coming to next one, in gray cast iron, carbon is present in the form flake, tempered, combined form as cementized or granular. Yes. In grey cast iron, we talk about flake type of graphite, and the tempered carbon is generally present in the your malleable cast iron. Okay, combined form as cementite, that is present in your white cast iron. We talk about Fe3C, and the granular cast type of graphite, it is present in the nodular cast iron. Okay, or ductile cast iron, which is also known as ductile cast iron. Your graphite carbon is present in the nodular form. So coming to next one, which of the element adversely affects graphite nodule count in ductile iron casting? So during the formation of that white cast iron, or sorry, nodular cast iron, we talked about some alloying elements addition in the system. Okay, to form the nodules of carbon inside the systems. So, anyone wants to answer? Hmm, you are saying aluminium. No, we have talked about it during the discussion on when we were discussing about nodular cast iron or ductile cast iron. In nodular, when we are going to make the nodular cast iron, we have to minimize the sulfur content in the cast iron as low as possible, because we have talked about the formation of iron sulfide. If sulfur content is more there, then it is going to create the iron sulfide in the system, and that iron sulfide is going to adversely affect the formation of graphite nodules count in the system. Okay, so Mg, Al, and zirconium, all three are added as a alloying elements. Apart from this, we add cerium and sodium also in the system to provide the foreign particles for creating graphite nodules in the system. Okay, but if sulfide is present there, then it will create your iron sulfide in the system, and it is going to adversely affect the properties of cast iron because it is having very high brittleness. Okay, so that material is not required in the system. We have to uh, get it lower down at around 0.05 or 0.10, less than that percentage, while making graphite nodule cast iron. Then coming to the next one, which of the following has maximum ductility? Grey cast iron, white cast iron, malleable or mottled iron? Yes. So the C is correct because we can convert that type of iron into a sheet formation. Uh, it is known as malleable iron because it has very high malleability properties due to the presence of that iron and perlite system in that system. And in grey cast iron, we were talking about flake type of graphite. In white cast iron, we were talking about the iron carbide presence. And mottled iron, I have no idea regarding this. I think, but malleable cast iron is definitely going to have the maximum ductility as compared to these four. That we can compare the malleable cast iron ductility with ductile cast iron also, because ductile cast iron also has a very high ductility. It can possess a elongation ratio of around 15 to 25 percentage easily. So that can be comparable with malleable iron, but none of these have a elongation ratio of more than 5% or so. Okay, so this is the end of today's lecture. If you have any doubt, you can ask. Yes, it can be as compared to others. Not that much you can provide that lower thickness, but you can convert them into seed, or it can show some formability. Actually, when we talk about stainless steel or mild steel, the major advantage of those types of steels are their formability. Okay, we can convert them in any shape. Okay, so with the help of malleable cast iron, we can go with that process. It will not be as comparable as mild steel or stainless steel, but in comparison to cast irons, it will be having much better property. Ductile iron is, yeah, yes, yes, yes. Because you have ductility, na, so you can go with the extrusion process or generally pipes are made with extrusion process, whatever I know. Okay, continuous extrusion process. You are going to heat your material and you are going to extrude it to form pipes. Okay, so with the help of ductile iron, you can create those pipes easily, and it will be having very high corrosion resistance properties due to the presence of graphite inside the system. So you can go with that. Yeah, it is done by it is done by not done by centrifugal casting because in because when we are going with casting process only, you are not going to uh, get that much of strength into your system. Okay, after centrifugal casting or whatever casting process you are going with, you have to go with some heat treatment processes uh, to impart the toughness or strength inside your system. Yeah. Okay, any more doubt? Satrujan, you want to ask something? Okay. Okay, thank you guys. So we will close our session and we will meet again on next Sunday. Okay, thank you.